real fast. We've got just a sweating. Think about when you was a kid, we used to play out in these all the time. Tachometers. Anybody heard that term? What does a tachometer do for us? Yeah, usually the rate is something we call it a tach or tach gauge. You have those. Some people have theirs on their car, which don't really mean anything because all our transmissions are automatic transmissions now. We have a tooth rotary, a direct current, and an AC current. And of course, we can use an incremental optical encoder to indicate what? Speed. So the faster those pulses are occurring, it's directly related to how fast something's in motion. The tax, we get tax all the time. Running things at precise speeds, especially on production lines, are very, very, very important. So it's pretty simple. We have a photo detector. We have a tach gauge, one of our tach gauges, to measure the speed of motors. Works on this exact same principle. What you do, you take a little reflective tape and you put it on your shaft. And then you turn your motor on. You take this little thing and you point at it, and then it tells you the what? It tells you how fast the shaft's going. Of course, the shaft and speed and the motor speed are the same. So all this is doing is just taking a photo, a light source, shooting it off. When it hits the stripe, it comes back and does what? Bounces back. And so it's going to be pulsing at you, and this would be almost exactly to what we would get off an incremental encoder, right? You understand? And all we got to do is count the pulses over a time. Of course, normally we don't count it over. So our speeds are rated in what? Yeah, if it's a rotary, it's rated in. If it's linear, it's feet per minute or meters per minute, right? But your rotary actuators are rated in revolutions per minute. So I could take the output of these guys right here, and then I could run it into counters. I could count it over 1 minute, and then I could display the count. I could reset my counters and go over. But now my display would only update how often? How often will my display update? Okay, so what we're doing is we're taking the output of this. Of course, we'd run it through some electronics, and then I would run this in the counters. And then what I would do is I would run this into units we call latches, which a latch is the count. Because if I didn't do that, the dang thing would update so fast I would never see it. You understand that? And then we would run this into a display. So my counters come up, but we're in revolutions per minute. So what I would do is I would have a timer every minute. It would come in and reset the counters and it would latch it and then reset the counters. But the problem is my display would only update every what? Minute, which is a long time. Have you ever just sit and wait for a minute to go by? But what could we do? This decrease the span, and normally if we go in 6, right? So let's say I count instead of 60 seconds, I counted for 30 seconds. Well, then what I do is I just double my count every time, right? You understand? If I counted for 6 seconds, well, then our count would be the same. It's just that we'd throw some zeros on the right-hand side. That makes sense? Yes or no? So that's normally what we do. We call it the gate, or how often we actually count. You can see it on a frequency counter real good because that's what they're doing. Over on the, which one was it? This one. So my frequency counter, this little flash light, that's how often it's updating the count. So you can see I can come over here and turn this knob, and it didn't move when I turned the knob. It waited till it did what? So if I've got a speed critical application, see what I'm doing? So I'm coming up here and turning. Watch how long it takes to update. It's not going to update until you see this thing right here flash. So if I'm in a speed critical application and I'm trying to count that thing for 1 minute, my motor speed could have increased quite a bit, and I don't see it until the next what? Into the next minute. But if I updated this thing every second, or every half second, or every third second, I changed the gate, then this thing here would respond instantly. And what we do, we add more teeth, we add more stripes, right? You understand? So if I put 2 stripes on each side, then I could count for 30 seconds, and it would still show me the same speed. If I put 3 stripes, right, you understand, then we could count 1/3 of the time, and then we would still get the same speed. So what we're doing is we're putting more pulses per count. That right? You understand? So if I had 60 stripes around there, then I could count it for 1 second, and it would still give me the what? It would still give me the right speed. And that's what we want on these tacks. We want it to be pretty accurate. But this, we could do this with digital. So this would be a digital circuit. So notice what do I have here? I have the encoder. We bring it in. Then I have, if you can see what I spelled right there, what do I have? Counters. And then what we would do is we would reset those counters, and that's exactly what's going on up here. What it does is oops, if I can get the glare off. So every time what it's doing now is counting. And then every time this flashes, what it does, it latches this display, resets the counters, and do what? Starts all over. But the problem is this is how fast we're counting on this thing. So that means what the problem is now is that we could do what? We could change the speed of the motor, could change the speed, and the slower you update it, the more inaccurate your system will be. Are we okay? Make sense? This would be pretty much the same. This is what's in your car, by the way. If anybody ever tore a transmission apart, there's a little old magnetic sensor up there. And what they're doing is they're changing the coefficient of coupling. So when this tooth comes around, we would get better coupling, right? You understand? When the tooth is in the center, we would get less coupling. So what this guy here would do is it would give us a little pulse out every time it did. I mean, it's AC, but it would be bigger every time a tooth came by, and then it would drop down when it's in the gap. So this is called a variable reluctance sensor. If you worked in transmission, odds are you would see one of these guys, because you got all types of gears in your transmission. And it doesn't make any sense to try to put an optical sensor in there or try to put this when these guys right here, they're extremely reliable. They don't care if they're in oil. They don't care, right? We just fill them up real good. And we just hook it up onto probably the main output gear of your transmission. So the main output gear of your transmission would be the one that's moving with your tires, right? You understand what we're saying? Yes or no? So yeah, if you worked on transmission, you'd probably see this little guy right there. This runs into your electronics. Used to, the way the speedometer worked is it literally had an old car. If you ever take an old car apart or an old motorcycle, you see it's got basically a cable that runs up from a gear assembly on there, and it runs up and came into the back of your speedometer. And when the tires turned, it turned a gear, and it spun that cable, and it came up and back into the back of your speedometer. The speedometer had a set of magnets that had one on the pointer up against a calibrated spring, and then it had these other set of magnets out here that spun with your tires. And what would happen is when those things pull by, it would try to do what? It would try to pull this other one, but a calibrated spring actually sets your speedometer. And now we don't have that anymore. If you take a car to get apart now and look at the speedometer, you're not going to see a cable coming up to it. You're going to see a what? My Honda Shadow used one of those cables, and the little gear assembly out there broke. And of course, I couldn't tell how fast I was going. The Harley Davidson I had an electronic sensor on it, but the cables ran under the seat, and by breaking the seat, it wore out those cables, and the speedometer stopped working. So we still have the same problems, but this works off this unit right here. So what happens is when this gear is spinning, every time it spins past one of these chunks of metal, what does it do? Puts out a little pulse, and then we run that into electronic circuits. So what do you see now? You see your speedometer. If you take all you're going to see is electrical wires coming to the back of that thing, because they use this variable reluctance pickup. And where's it at? It's inside the transmission. Well, the old speedometer was still inside the transmission, but you were dealing with gears, right? Actual physically setting the speed. What's nice about having the seat set with electronics is that now, of course, your speedometer is not fed directly from your speed sensor. We have a computer inside our car. Most cars have two of them in there now. One of them they call the ECM. What's the ECM? Engine control module. And then we have the BCM. What's the BCM? The body control module. So your car now has two computers in them. One of them's in there running your lights and all your. So on my car, I can get out of it and it turns the lights off for me automatically, right? You understand that? When I get out, your dome lights come on, and when you get out and close the door, they don't go off. They do what? Yeah, they time off, and they don't just turn off; they fade off. Yeah. So if I open my door with my keys in my ignition, what does it start doing? Yeah, it starts beeping at me, indicating you're fixing to get out of the car and leave your keys in it. So it's pretty neat. So this runs in there. But what's nice about this? Not only can it sense, not only can we use it for our speedometer, we can also use this for our cruise control. Everybody okay here? We had this over there, but it got thrown away. We had I think it was a Seco with a SCR drive for a DC motor, and this is what they use to sense the speed on it. They use one of these reluctance pickups. Worked really, really good. The problem we have is that it has problems with extremely slow speeds. But mature bit technology operates at very high temperatures. We can operate these things in harsh environments. It just has problems picking up extremely slow speed. It's like your car. You can literally move your car and your speedometer never gets off zero because you're below the resolution of this thing, right? You understand that? We okay? Questions? This is what a variable reluctance pickup looks like. Like I said, it's sealed up real well. Got a connector on the back. They can seal that up. And then normally you'll have a little pin on the front of it. It'll have a little metal button, which is actually what goes down. And you have to adjust these things real close. You have to get them extremely close to the gear that is trying to detect the speed of. DC tax. It's nothing but DC generators. You know how DC generators work? So all we got to do is do what? Usually these are not regulated. They're permanent magnets. Get to my box. All those parts in there. I don't know if I got a little DC motor. What's nice about a DC motor? A DC motor and a DC generator are basically the same. Now you can use a DC motor, you can use it as a generator, or you can use it as a motor. Well, what these things are, these are what we call permanent magnet DC motors. And what that means is that all you have is a set of permanent magnets in there. And they usually wrap around these things. And then you have a wound rotor in the center. And then when it spins, it causes the wires to do what? Move through the magnetic field. So we've got wires, we got a magnetic field, and we have what? Motion. So these would induce a voltage into the little coils. The problem is by default, the voltage that these guys put out are going to be AC. No, I don't want to do that. I want to go to so what we have on the motor is we have, this is called a commutator, and I'll try to show y'all ones. Right now I can't get to my box. It's got all my stuff in there. It's all covered up. So by default, if I just put that thing and spun it and brought it out through some slip rings, it would put out AC. But what we do is we use these brushes. Can y'all see them right here? I don't know if you can see it or not. And this is not animated. Then you split this, and what happens is brushes, we call it brushes, the brushes are stationary. So what happens when this thing here spins, what are they constantly doing? Can y'all see what it does? It constantly changes, well, it doesn't change, it constantly switches over to the right polarity, right? You understand that? What happened to my screen? I want that one. What do you mean? We're not talking about motors, we're talking about generators. Yes, an AC generator has brushes in them, and a DC generator has brushes in them. The only difference being is that on an AC generator, we don't switch the leads. We keep whatever we get off of them. Because what happens is that, so we got a magnetic field. And of course, the polarity of this magnetic field is not going to change, right? You understand? So if this is moving in this direction right there, okay, then what happens is when we move up in here, we get one polarity. Then if we swing down through here, we go through them in the opposite direction, right? So here we're going through the magnetic lines of force from left to right. Here we're going from what? Right to left. So what would happen is that we would get this right here, which is AC. And what would determine the amount of AC is how fast we move it. And then plus AC, not only are you going to change the volume, you're also going to change the frequency. So what we do on DC is we have a little unit out here. We let the generator do it itself. So if I was to come up here like this, and I was to take the output of this thing, right? Y'all understand this? And I had this switch. So here's my output. Okay. And what I do is my switch would look like this. So when this was a positive and this was a negative, I would have this. It would be a two position switch. But I would put this up here. When this changed polarities, this went positive, then I would switch that down like that. Right? You understand? Well, then what I would always get is I'd always get positive. I would get this guy right here. But I would have to switch it in sync with the generator. Well, good gracious, the generator's in motion. Why can't we let the generator switch it for us? Y'all understand that? All I've got to do is here, what would I have to do? I would have to do what? Switch it, but we can let the generator switch it. So if I came over here and put these two things like this, okay, and I put, we call them brushes, so these would be made out of copper, and then my windings coming out of my my rotating part would be connected to the brushes. Well, when this was positive, this would be negative, right? You understand? And then when this one went positive, this would be negative. It's already going to rotate around here, so this brush would always be positive, and this right here would always be negative, right? You understand? But what we're doing is we're letting the generator do what for us? Switch it. And of course, if I came over here and put another set right there, right? You understand? Then what would happen is that I would fill in these gaps, because now I'm not making an entire revolution to swap between the two. We would have them. So when you look at a commutator, you're going to have a lot of segments on it, right? You understand? And what that does is that it comes in and fills in the gap. So what I would do is out of the generator, you'd see little ripples at the top, but it would be DC. Not pulsating anymore. It's going to be DC. It's just that you'll have a little ripple up there on the switching, and that's not really true. The way the thing works is that it actually is between two segments at the same time. If you ever looked at a brush, it's actually looking at two segments at the same time. So basically, it puts out a really nice DC. And what determines the amount? Well, we're not changing the number of coils in the secondary. I mean, on the rotor, we're not changing the number. We're not changing the strength of the magnetic field. So what would determine the speed of the motion? That's the three things, right? You can either change the strength of the field. Well, these guys use permanent magnets. What's the difference between a permanent magnet and an electromagnet? Well, a permanent magnet has the same magnetic field all the time, right? You understand? I'm not changing the number of white coils that I put inside the rotor. But this is a DC tach. So that means you want the output to change, but what's going to change the output? The speed of the motion. Let me go get one of these guys. No. This has an AC tach on it, but what I want to do is I want y'all to actually look in and see the commutator. I'm going to try to get one that's opened up a little bit so y'all can see it. Now, these things are really, really sealed up. So you so they can be operated in all types of environments. But you can tell because you can take something metal, and if you come onto the side, it should stick onto it because there's permanent magnets inside this thing. So when we pass this around, I want you to look so you can actually see the brushes right here. So here's a little brush holder right there. Okay. And then you can see the wire connected to the brush holders. These little slots in here, by the way, these are what's holding the permanent magnets into place. You don't have to screw the things in because this is a ferrous metal, and basically they just clamp up there. Sometimes they glue them in. But when you look real close, you'll be able to look down and see the commutator down here. And what that thing does is when this thing here turns, it automatically switches it every time to make it output a DC. So I can literally take a meter up here and I can spin this thing with my hand, and we would see the meter change. And the faster we spin it, the more voltage it would put out. The slower I spin it, the less voltage I put out. And these guys here work over an extremely wide range of speeds. And by the way, this is not a tach generator, this is a DC motor. But a DC motor and a DC generator are basically the same thing. And it dawned on me one time, we had a jet when I was in the Navy we was working. It was a little Learjet that they flew, and they was having problems with cranking the dang thing, and they used the generator was the starter. So they didn't have a starter and a generator. They had a DC motor out there that they used to do what? Start the dang thing, and also do what? Get power off of it once it started spinning. So I could literally take that meter right there, and I could hook that thing up to something. And then what I would do is I would try to get the transfer function. Here we're going to have volts per RPM, right, or something like that. So that would be very easy, volts per RPM. I don't have to count anything. So if I get 3 volts out of the thing, that's going to represent a what? An RPM. And that sucker changes instantly. So if the speed of the motor changes, the output of that tach generator is going to change immediately, right? You understand? We don't have to count anything. So these guys are used a lot for tach, sensing the speed. Now we have these things hooked up to motors all over the place. When you get into production, you know, when you run that production line, normally it has to be at a precise speed. If you go too slow, you're costing money. If you go too fast, then the other devices cannot pick up with it, or it just can't work. When the number 4 galvanizer line, when you dip that tin plate, that metal strip down through that zinc, it had to go through there at a perfect speed. If it went through there too slow, then it would put too much on there, right? If you went through there too fast, it wouldn't put enough on there, and you would have problems. And you didn't want too much because then it wouldn't get through the rolls and stuff like that, or you couldn't bend it. So most of your production lines, when we move at a precise speed. So these robots over here, we have the ability to tell the speed we want to move it at, you know. And by George, how does it know it's moving at that speed? Well, it's got to have some type of sensor out there that says you're going at that speed. So you got your car, you're cruising along, right? You say 70 miles an hour and you hit that cruise control. How does it know it's going at 70 miles an hour? Well, there's got to be a sensor out there that says, so you say, I want it to go this fast, and your sensor comes back and says what? I'm going at that speed. Of course, they don't use a tach generator. They use that pulsing. They use that variable reluctance because that guy, the faster the pulses come back, the faster your car is going, right? Can y'all actually look in there and see the little commutator plate in there? So what happens is when it switches, what's it constantly doing? It's constantly switching to keep the polarity on the output of the little generator the same. And this is not, we don't want this guy to be regulated. So all it does is use what? Permanent magnets. And what determines the amount of voltage we get out of those things? It would be directly proportional to what? Speed. And that's a DC tach generator. If you get out and you work on DC drives, odds are it's going to be a DC tach generator. If we work on AC drives, odds are it's going to be a what? A tach. This is a MG. This is a little motor. What's nice about this little motor? This guy here has the tach generator built into it. So notice we have 4 wires coming off of it. 2 of them are for the motor, 2 of them for the tach generator, and it's actually one unit together. This used to be back in the old days of y'all read the article that popped up about the nuclear program is still ran by floppy disk. Did y'all see that article? We still got some floppies around here, by the way. But this was actually the motor that ran one of these floppy disk drives, and those guys had to run at a precise speed. So we had a motor that we ran, and then we had a tach generator, and there were so many of them that the tach generator is actually built into the motor, which is pretty neat. It's nothing but a DC motor, but it's all sealed up, so you can't. So there's the motor itself, and if you look at it, you got one end would be the motor, and the other end would be the tach generator. So if I came over here and ran this thing, I'm looking for some wires. I know it's time to go, guys. I think the red and the blue is the motors. Oh, wrong camera, Rich. All right. I don't see my wire stripper, so I'll have to cheat on it. Strip it off a little further. That's not a good way to strip wire, because if you nick the wire, it's a solid strand wire. If you nick it, then it's going to break real easy. But if you've been doing it for years, you can do it. So we'll get up to a DC power source, and we'll see if we can control speed. And we'll look at the tach generator. Crap. But my wire fell out. I don't see it. So you see the motor's turning. Right? This is what the advantage of the DC motor still has over an AC motor, is that we can precisely control a DC motor. Don't you hate when you do that? Huh? What did I do with my cutter? No, I didn't get up. Might have been in my front pocket. My cutters. What I just had in my hand. Ain't that something? A blue hand, not pretty little blue handle. No, that's oh, there you go. Ain't that amazing? Here they are. I'd have never found them. Yeah, yeah, no, they they had fell down right here. Our glasses. You ever look for your glasses and they're up here? Okay, so what? Call somebody. Say, I didn't see my cell phone. This I'm gonna use a resistor for this other one. I'm sure. I'm trying not to sort this out. Hmm. So this is a DC tag. I'm sorry, this is an AC tag. So if I increase the speed of the motor, what should we expect the output to do? Huh? Yeah, what's nice about an AC tag is we got two things that we can use to represent the speed. Notice not only is the amplitude changing, but also the frequency. So the frequency would work real good in a digital application, right? I could very easily take those and turn it into a series of pulses, and it would work real good in a DC application too. I could take this output and run it into what we call a rectifier, and I could very easily take the AC and convert it to DC in a heartbeat. So an AC tach generator has two functions we can use. Works real good in what? Digital. So if I brought it into a digital thing like a PLC or something like that, man, it'd be nothing, right? We could set up a counter, bring in this pulse that's coming off here, bring it into a PLC, run it into a counter. Anybody said PLCs? Even though we're sitting out and then count those things over a certain amount of time, come up and give you the RPM and nothing at all. But if I was going to run it into a DC type of drive, then but we could just take this and run it into a device that converts what? AC to DC, and we could use this in either a DC system or an AC system or a digital system. We could use this in a digital system. Yeah, this would be a snap to convert to a digital. Now that's my tape, by the way. Now this thing here is really neat. It's an MG set. I could do the same thing with this guy, but this guy would vary with what? Its output would vary with speed. Now you have to understand this is 2 units in one. This is an MG. It's got a tack generator in it and a motor, and this was in a speed control system. And it controlled the speed of the floppy disk, how fast it spun the disk around. They use a Hall effect sensor to sense speed. We'll look at that later on too, Hall effect. And what it is it picks up a little magnetic field. So what they have on their motor is they have a magnetic field that it picks up, and they use that to judge the speed. The old 3.5-inch floppy drive went to the Hall effect sensor for the speed. This was the old 8-inch. They said some of the nuclear systems in the country are running off 8-inch floppy drives, which could only hold 128 kilobytes worth of data. And that's running the nuclear system here. They're talking about upgrading it. I mean, all the rockets and all the nuclear missile systems are being ran by floppy drives. So all the information, everything is saved on floppy disks, not even hard drives or solid state drives. A lot of your laptops are actually going away from hard drives. They're going to these solid state drives. Well, you can't get near the transfer speed off of them. These devices. Well, even on laptops that's got hard drives, you can never get one as big as the 5 1/4. The 5 1/4, that guy's got terabytes. Here we're still lucky if we can get 800 1 terabyte worth of storage. That's 6 terabytes right there. Six terabytes. That's a billion. So everything our department does is on this little black box right there. And it's 6 terabytes worth of storage. Yeah, that is. That's a Tera server. 6 terabytes worth of storage, and we're maybe using not even one yet. So that shows you what a terabyte is. So we got a lot of space. So okay, so what we'll try to do is we'll try to set up some labs that will work. Y'all might have to help me write them. Tell them to do that. Like this is y'all the guinea pigs in this class. But we'll try to do a lab on a pot. Of course, y'all gonna be y'all be the right. Well, you're gonna have to turn the pots. We're not gonna hook them up to something. We're gonna judge your position. Yeah, you'll be the hamsters. And then we'll set up a lab where you can actually look at the full range of the pot. So the span would be the full range, right? You understand that? And then we'll set up a span. So we'll hook it up between 2 resistors and actually get a span. So normally a pot we would go. So if we hooked it up to 10 volts, we would go from 10 volts down to 0 volts. But I might not want to go from 10 volts down to 0 volts. I might want to go from 5 volts to 3 volts, right? You understand that? So we have the ability to show you how we can set the span on those things. What is the span? The range for the output, right? That we allow them. Okay, guys. See y'all Thursday. I was listening to my tape recording, and I roll around so much. By the way, most of my tape recordings you're going to have headphones to listen to, because normally I use my speaker on my microphone on my computer. So when I started listening to it, that's why I went back to this thing right here. So now you should hear me, even when I don't want you to hear me, right? Yeah, but I couldn't leave today, get off. No, we don't have the wire that small. Yeah, all our wire, most of our wire is stranded. Uh, we have to get a bunch of the heater. We got one the heater we got one fit into this, one fit into the one go around the connector. You don't want to use tape because tape will wear out after a while anyway. You know, all the small gauge wire we have is solid strand wire. You wouldn't want to use solid strand because it would be flexible. You want so strange, some of it's not affected at all. Well, it depends. No, well, it's not just insulation. So whatever insulation that they use on this, did not get wrong with it. Looks like it didn't get wrong with the plastic of the robot. Whatever it is, whatever type of plastic that is. It was, we didn't buy them at the same time. We bought them within a year of each other. You can see this guy here has a different plastic than this guy. Yeah. And that's the only thing I can figure is that they figured out whatever plastic they used here didn't go with the wires that were inside the robot. And you can see with black almost all the wires that would come back in here. Look at that, amazing. That's been a year. So this is this part right here. So they had to use different type of plastic because these two robots are basically together. And look how much this plastic right here is yellow, inside and out. That's what they had to do. And they had to change their plastic from this model to this model. I mean, they have been right here together. They stood side by side for years until this guy started to messing up. It looks like they messed whatever this is made out of. It looks like they messed two different types of plastic. Look at that. So this and this and this, I guarantee it had something to do with whatever it was, whoever made this form. They probably had, I don't think they had the ability to do the injection molding, so they probably had to clean up different places to make parts for them. But I think that's interesting. This guy here's no problem. But yeah, what we'd have to do is, and this is the problem, we have to, these right here, yeah, it's all in there. And even if it looks good, all it takes is stuff like that. So we have to replace all this wiring in here. So we don't even have it tore down far enough yet to be able to do the work. All we have is and this has a different type of insulation. This has a different package. That's why this is a different wire. This has a different type of wire. And we're talking a long time. Oh, we need to get this. We need to get this wire. You good at soldering? I'd have to check it out. Oh, yeah, you took the, you took the, we get a little more detail in the troubleshooting class.